Welcome everyone. Today we are going to discuss about packing circles onto a square. How can you arrange identical circles compactly and concisely inside a square without overlapping? Like you have to place identical circles in a square in such a way that the number of circles arranged inside the square is maximized. So you have to be efficient in your arrangement. In what way should I arrange them? Should I arrange them in rectangular way or should I arrange them in hexagonal closed packing? Let's take a look into this problem to understand it further. This was a problem from level 3 of fortnight 27 in our SuMON math program. Our students showed a lot of enthusiasm in solving this and they came up with their own innovations. If you get some more ideas, you can add in comment box and let's get started. Here is the question. You are asked to draw a square with side length 10. Like this. You are going to cut out several identical circular coins of diameter 1. The diameter is 1. Assume there is infinite supply of these identical coins. You are going to place them on this square, 10 cross 10 square. How are you going to arrange 100 identical circular coins onto the square without protruding out and without any overlap? And how are you going to arrange 102, 105, 106? First of all, is it possible to arrange 106? We even don't know that. Let's give it a try. First of all, arranging 100 is not that difficult. You just gonna place the circular coins, 10 circular coins, one by one in the first row. This is the third one, fourth one. You keep all the way up to 10th one. And of course, they can be arranged this way. Like they are tangential, one after the other in first row. Next, consider the second row. You are going to have circular coins arranged one beneath the other in the second row. And this is continued for 10 rows. So they are compactly arranged, but maybe it is not the most efficient way, which we will come into. But as far as simple idea is considered, by a simple look, one can say that this is compactly arranged. And this has total 100 coins. What about 102, 105, 106? First, whenever I see this kind of arrangement, I get to remember the hexagonal closed packing of atoms that I studied long back, in which you have atoms arranged in hexagonal fashion in order to make the arrangement too compact and consume as less volume as possible. So why don't we try to implement that here? What if hexagonal packing is more efficient? Let's see. Hexagonal packing is simple. You have coins arranged in the first row, same as the previous arrangement, and so on. For the second row, you are going to decrease this gap that is caused vertically. How do we do that? Instead of arranging them one beneath the other, we are going to fit it in the gap formed that we mentioned. Like this. This decreases the vertical gap of the second row and the first row. So you have up to this part. Well, we are not being quite efficient in terms of horizontal space. I do agree on that. But we do not know how efficient we are by saving those vertical spaces that is formed here in these gaps. We will get to know that once we compute them through numbers. Alright, coming to the third row, we start with the original arrangement, like the first row. So we mimic the first row and it extends up to this point. Now the reason why it's called hexagon can be identified here. There is a hexagonal formation in this compact arrangement. Now for the fourth row, we repeat the second row. So like the first and second row, copy of first and second row are repeated together up to the last. Since we are making it more efficient vertically, maybe we are able to add one more row when compared to the previous arrangement. In the previous arrangement, we had 10 columns and 10 rows, which was a rectilinear arrangement. Not very complicated. That was very simple. But this one doesn't seem very simple. Since we are efficient vertically, maybe we are able to add 11th row. And if we are able to do that, we have achieved something substantial, right? So let's see how much the first and second row together occupies. Notice that the centers of some 3 circles that are mutually tangent to each other form an equilateral triangle due to identical circles. So if half is the radius of one circle, so the total length will be the sum of radii of those 2 circles, which will create an equilateral triangle with side length 1. And now you see that the height of that triangle is root 3 upon 2 by simple trigonometry, because sine 60 is root 3 by 2. Or you can use the fact that altitude bisects the opposite side and use Pythagoras theorem to derive the height is root 3 upon 2. Okay, if that height is root 3 upon 2, then this distance, let me draw that separately. So you have one circle like this, another circle like this, and third circle like this. These 3 are identical, and this is the equilateral triangle we are concerned. Notice that the entire height can be divided into 3 parts. One is this one, this height or the radius of one circle, and the second, the height of equilateral triangle, third, the radius of the top circle, the bottom circle. So the radius of top and bottom circles are half and half, and the height of equilateral triangle is root 3 upon 2, and they add up to a total height of 1 plus root 3 by 2. Okay, the height of one stack or two rows is 1 plus root 3 by 2. Alright, now you see that every new row that we add adds up additional vertical space of root 3 upon 2. The first row occupies one vertical height, 1 unit of vertical height, because the diameter is 1. The next row occupies only root 3 by 2, which is less than 1. So therefore we are optimizing it that way. Next, the third row will also optimize the vertical height by occupying those gaps, and that adds only root 3 by 2 more of vertical height. Now similarly, when you add the next, the additional, which the next row, the fourth row, will be identical to the second row, and it will also be tangential to each other, and it also adds root 3 by 2. In order to find the total number of rows, maximum you can add to not protrude the square can be identified by the maximum number of root 3 by 2's that you can add to 1 to stay less than or equal to 10. And that will be the number of additional rows apart from the first row. So computing this, you will get k to be less than or equal to 10. So you will get k to be less than or equal to 10.39, but since it's an integer, we will have it less than or equal to 10. And the total number of rows is 1 plus k, which is at most 11. Thus, we have optimized it in vertical way, but definitely we have lost some space in horizontal way, because the second row is now occupied by only 9 identical squares, not 10. So horizontally we are losing some count, but vertically we are gaining one more entire row. So the last row will be identical, the 11th row will be identical to the first row. So it will look like this. Over here, the total number of squares will be 10 plus 9, and this repeated 5 times. The stack of first and second row is repeated 5 times, amounting to 10 rows in total, and the 11th row will have 10 additional squares. This is 105. Hence, by optimizing vertically but losing a bit horizontally in the second and fourth rows and so on, we are able to arrange 105 identical circular coins. So that means you can arrange 102 as well as 105. Now, for 106, is it possible? The answer is yes. By using some combination of hexagonal closed packing and rectilinear packing, you can make 106 as well possible. Now that is given to you as a homework. Try it and comment out your ideas in the chat box. So we deliver to students a lot of such interesting problems with which they can play around. If you are interested in solving such problems, join us through trial application at www.sumon.com. See you in the next video. Thank you. Bye.